If the materials inside modern electronics suddenly vanished, power grids would collapse, communication networks would go dead, and the global financial system would freeze instantly. Before controlling electricity at microscopic scales, electronics relied on vacuum tubes. These glass components controlled current, but they were massive, fragile, and generated immense heat. The successor to the vacuum tube was silicon, an element found in common sand, refined here into crystalline chunks. In this pure form, silicon is naturally inert. It resists the flow of electricity at room temperature, making it a poor conductor in its raw state. Modern civilization operates through humanity's ability to manipulate the microscopic, invisible spaces between these silicon atoms. Within a pure silicon crystal, atoms form a highly stable, diamond-like lattice. Every atom shares its 4 outer electrons with its neighbors, creating a rigid network of covalent bonds. Quantum rules dictate that these electrons can only exist in specific energy states. In this stable lattice, they are bound to the atoms, trapped in the valence band. We can map these states. The valence band holds the trapped electrons, while the conduction band above it is where electrons can move freely to create a current. Between them lies the forbidden gap. Insulators like glass have a massive gap that blocks electron movement entirely. Conductors like copper have overlapping bands, allowing electricity to flow. Silicon sits between these extremes, with a narrow gap of exactly 1.1 electron volts. Ambient thermal energy can occasionally excite a single electron across this 1.1 eV gap, but the resulting current is too weak and erratic for complex technology. This 1.1 eV threshold provides a precise energy barrier. It's wide enough to prevent random electron flow, yet narrow enough to overcome with deliberate engineering. Because random heat is too unpredictable for logic circuits, we require absolute control over when and where the current moves. Scientists achieve this control through doping, the deliberate injection of specific impurity atoms into the silicon lattice to transform its electrical properties. Injecting pentavalent phosphorus introduces a free fifth electron, creating N-type silicon, where electrons are the majority carriers. Conversely, trivalent boron has only 3 valence electrons, leaving a vacancy in the lattice. This creates P-type silicon. This vacancy, or hole, acts as a positive charge carrier. It accepts electrons from neighboring atoms, allowing the hole to move through the lattice. This process transforms inert silicon into 2 distinct controllable materials, one dominated by negative electrons, the other by positive holes. The most critical electronic behavior occurs when these N-type and P-type materials are brought together. At the P-N junction boundary, electrons and holes diffuse across and neutralize each other, leaving behind a layer of immobile charged ions. These ions create an internal electric field that repels further charge movement, forming a depletion region, a microscopic wall blocking all current. We can manipulate this wall with external voltage. Under forward bias, the applied energy crushes the barrier, allowing a massive flow of current through the junction. Reversing the voltage expands the depletion region, widening the barrier and blocking current entirely. This microscopic standoff creates the essential quantum valve that allows humanity to dictate the exact path of electricity. This single quantum valve is the basis of the first transistors, replacing bulky vacuum tubes. Using these junctions as high-speed switches transformed consumer electronics, enabling devices like the portable transistor radio. Manufacturing eventually moved to integrated circuits, where millions of junctions are etched onto simple silicon wafers. Today, this basic physics principle is scaled by the billions. Microprocessors now contain vast arrays of these junctions, performing calculations millions of times per second. These principles operate everywhere, from home computers to the solar panels of satellites in deep space. Global networks, financial grids, and medical scanners operate through our absolute mastery over the invisible quantum spaces between these atoms.